Good afternoon, everyone. Welcome to the another session of problem solving, design of reinforced concrete structures, week 10. This session is scheduled from 3 to 4 p.m. As you have already gone through the lectures posted in the online website NEPTAL, in week 10, torsion is being discussed there, and it's almost complete. Now you will be shifting to footings or something else. Today we will be also discussing torsion, and we will solve a design problem regarding the torsion effects. So in torsion effects, you would have studied there these definitions: primary torsion, secondary torsion, and all the theories regarding the torsion and the behavior of the plain concrete in torsion, as well as reinforced concrete in torsion, and why we need torsional reinforcement and what are the detailing. Today we are directly going to solve a design problem regarding the torsional reinforcement. Remember one thing, torsional reinforcement is not something different. It's same as we discussed it in the shear reinforcement. For shear we provide the stirrups. Same in the case of torsion, to resist the torsional effects we provide stirrups. And we have to see the shear and torsional effects we have to see the shear and torsion effects in combined form, and we have to then design the torsional reinforcement for the combined effects, both shear and torsion. So for that, code has given the equivalent definitions of the shear force, equivalent shear force, and the equivalent shear stress that comes due to the torsion effects as well. I will write the formulas directly. So you can see in the code clause 41.3.1, they said the equivalent shear that comes when there is torsion effect also considered VE that you have to calculate as VU, nominal shear force, plus 1.6 times TU by B. Okay, you can see that in addition to nominal shear VU, there is an additional term 1.6 times TU by B. This is due to the torsion effect. Due to torsional effect. Now this equivalent shear force will create equivalent shear stress as well. So the shear stress that will come due to this shear force will be equivalent shear force tau V equivalent. It will be given as same shear stress, shear force VU plus 1.6 TU by B divided by area of cross section, B width of the section, D effective depth. Okay, this is just the basic formula you have to remember in design. And torsional strength with torsional reinforcement, there are different theories for this. One is the space truss analogy. It's discussed in detail in the online lectures available. And another is skew bending theory. It's also discussed there in detail. And there are then IS guidelines, IS code guidelines for the design of longitudinal reinforcement and the torsional reinforcement as well. These are also discussed in detail. I will only touch a design problem for that thing. IS code says, let me first, it will be a bit difficult if I will not discuss this formula. IS code says that if there is torsional effect also, the effective bending moment that you have to consider on the section MT will be given by this formula. It is TU plus 1 plus gross depth D divided by width of the section B whole divided by 1.7. 1.7. Okay, 1.7 from the it's actually from the skew bending theory, that this torsional moment, this can either add to the original moment acting there, or it can subtract it from the original or the effective moment that's acting due to the transverse loads. Actually, it has four modes: mode 1, mode 2, mode 3, mode 4. Depending on any of the modes, this torsional moment can either add up to the already existing moment, or it can be subtracted from that moment. For that, you have to consider both the cases, so that the M equivalent will be M torsional plus minus mu. Okay, you have to consider it like that. And then we have to consider ASV also, area of the stirrups, considering the torsional effect as well. ASV, there is a formula directly given by code. ASV is given as uh, torsion moment into SV. SV is the spacing. B1 D1 0.87. Fy is the grade of the steel plus Vu nominal shear force acting. SV spacing adopted. I'm telling the what each symbol means. Okay, 2.5 D1 into 0.87 Fy. Now this B1 D1, I will make it clear what this B1 D1 are. This B1 D1 are this B1 D1 are these things. For example, we have a section like this. Originally, our width of the section is defined by this width. Okay, outermost distance between the outermost edges like this B. But when we have torsion, also we require another definition of the width of section, that's B1. That B1 is given as the distance between the centroids of the longitudinal reinforcement. So the B1 here will be given by this distance. Distance between the centroids. Okay, B1. So if we draw like this is B1. And same like at the bottom there will be reinforcement again, like this one here and this one here. We know that the effective depth is defined as depth from the top face up to the centroid of the steel, bottom steel. Here it's the centroid of the bottom steel. We define it as D. But another definition comes in play, D1, that we use in formula. It is distance between the centroids of the longitudinal steel when we measure it along the depth. Okay, this becomes your D1. And another thing is, there is one more thing, x1 y1 depths. Okay, x1 y1 depths you have to measure. Then there will be this, you will provide a shear reinforcement like this. These definitions are only applicable when there were torsional effects also. We provide shear reinforcement like this. Okay, we define another distance x1 y1. x1 y1 is the outermost face of the stirrup, outermost side of the stirrup. On both sides we define it as x1. Okay, sorry, we define these distances as x1. I will use these terminologies in subsequent formulas. x1, and we define, if we measure it at along the depth, we define it as y1. Measuring it along the breadth, we define it as x1, and measuring it along the depth, we define it as y1. Okay, these x1 and y1 are the short and long center to center dimensions of the rectangular closed stirrups. I will write here x1 comma y1 short and long, short and long center to center, center to center dimension, dimensions of rectangular closed stirrups. Okay, this is thing. Another formula from the code is spacing of these stirrups should be less than any of these. SV should be less or equal to, either it should be less than x1, either it should be 1/4 of x1 plus y1, or it should be 300 mm. Minimum of any three you have to take. After you calculate the spacing, we calculate actually spacing from this formula. Okay, when we calculate spacing from this formula, we then check it, cross check it with the formula from the code, and then we decide on that which we have to take as minimum. Now we will come to our design formula problem. Our problem is like this. Today is week 10, problem 10. Problem number 10 we are discussing today. So today what is given in the problem is that a beam framing between the columns has an effective span of 5 meters and supports a cantilever portion 1 meter wide throughout its length. Assume that the cross-sectional details of the beam are exactly same as this. Determine the adequacy of this section as per IS code, assuming total uniformly distributed live load and cantilever project. Assume fixity at the ends. Okay. We will check this section. Okay. We are given a beam like this. Okay. We are given a beam like a beam is spanned between 2 points like this one. Okay, if I have this rigid fixed joint one side, a beam is running from this one to another fixed joint. So one fixed support to another fixed support like this one. Okay, this beam is from this support 1 to support 2, support 1 to support 2. Obviously the beam has some depth and width as well, but I am not showing that. What is that beam is subjected to downward load, okay, UDL, like this one. Okay, it is obvious from the figure that this is gravity load acting downwards. In problem it is given that this load acting is uniform WU as 13.13 kilonewton per meter. Okay, and there is torsion also acting. I will show it different. It's acting like this. Okay, it's acting like this. Actually, from where this torsion is coming, actually this is a beam, this is a beam like this one. This beam, actually it is supporting a cantilever projection like this one. It is supporting a cantilever projection of 1 meter wide. It is supporting like this from this side. It is supporting cantilever projection like this from this side. Okay, this will be like this, a small little depth at the free end, some depth at the fixed end. Due to this, if this has some, this cantilever projection will be having some load, weight due to self weight. Okay, maybe self weight will be acting like this all along it. So if we see that this cantilever projection is inducing some torsional moment. Due to this, this is inducing some torsional moment into this beam. Okay, just trying to rotate it like this. Okay, that is the thing I have shown here. This is the same thing I have shown here. Okay, you have to look it like this. So the figure is like this. We have a beam. I'm showing it from the side one. We have a beam section like this. It is, I will write the dimensions later. And cantilever projection like this. Cantilever projection like this. And on cantilever projection, 5 kilonewton per meter square. Like this, 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 this one. Okay. 5 kilonewton per meter square is the total dead plus live load from the cantilever projection. Dead load plus live load, both from the cantilever projection. And our beam dimensions are, beam and projection dimensions are, it is, this is 500 mm gross depth and it is 300 mm width, and cantilever projection is 1 meter long, that is 1000 mm. Okay, 1000 mm. So there will be torsional effect coming on this main beam as well, so we have to consider that as well. So if we see from, since the beam is fixed from both ends, I will draw the bending moment diagram. Bending moment diagram for the fixed and beam will be like this. It will have a bending moment like, some bending fixed end moment like this, some hogging fixed end moment like this, and there will be sagging moment like this. Okay, we will have this area, this area, this is, we will be having moment mu here as, it's w u l square by 12. Okay, sagging moment here, it will be half of this all structural analysis, w l square by 24. Okay, and the same shear force diagram for it will be like this one. Okay, so we will have a shear force Vu, it will be Mu. We will have shear force Vu equals WUL by 2. Okay, it's a uniformly distributed load, it will be Mu here. And there will be also twisting moment. Twisting moment, it's a uniformly distributed twisting moment acting on it. So the twisting moment diagram will be like this. This one, this one, well, like this. Okay, we will have TUS TUS by 2. Okay, so we'll calculate the different quantities. We have all the details. So first section will be loads. Loads on beam. So loads on beam, first from projection. From projection we can see that projection is like this, this and this is the projection. I already showed you 5 kilonewton per meter square. Remember, this is per meter square, and we have given this width. Okay, this is 1 meter. So if we want to calculate the distribution of this load along this length only, we have to multiply by this length. Okay, it will be from projection, it will be 5 kilonewton per meter square into 1 meter. Okay, it will come out to be 5 kilonewton per meter. So from surface load, it changes into uniformly distributed line load. So it will be acting along this, like this one. Okay, this will be now 5 kilonewton per meter. Okay, from self weight, of this 5 kilonewton meter will now come on beam directly. From self weight, it will be 25 kilonewton per meter cube unit weight multiplied by beam dimensions. 0.3 meter is the width and 0.5 is the gross depth. This comes out to be 3.75 kilonewton per meter. Okay, when we sum it up total, we get it as 8.75 kilonewton per meter W. Okay, uniformly distributed load acting on it. So the factored load acting on beam, we denote it by W subscript to U as 1.5 as load factor times W 8.75. It comes out to be 13.13 kilonewton per meter. Okay, also we have to now calculate eccentricity. Eccentricity of cantilever load. Because it will induce torsional moments in our beam. Cantilever load will be equal to, okay, firstly it will be half of this distance, 1 meter divided by 2, and from its beam here also. Okay, beam, so it will be half width of beam, this plus half of the cantilever projection. It will be 1 meter divided by 2 plus 0.3 divided by 2. Okay, 0.65. Okay, 0.65 is the cantilever projection. So the factored distributed torque that will be acting, factor distributed torque TU will be, firstly it is the surface load 5 kilonewton per meter square acting on a surface multiplied by the eccentricity 0.65 meter. It will become the UDL times 1.5. Okay, it will come out to be 4.88 kilonewton meter per meter. Okay, maximum. So now we have stress resultants we have to calculate. From these forces we will get the stresses on our beam. So stress resultants are Stress resultants. Firstly, the maximum twisting moment. Max twisting moment. Maximum twisting moment TU will be torque TUL by 2. I already showed you it in the this diagram. Maximum is here TUL by 2. Okay, TUL by 2. We have 4.88. Length is 5. I already told you its effective span is 5 meter. This is 5 meter. Okay, 5 divided by 2. We get a value of 12.2 kilonewton meter. Okay, max bending moment also I showed in the bending moment diagram. Maximum bending moment, that is the hogging moment at support. We get that as mu wu l square by 12. Okay, when we plug all the values we get 27.35 kilonewton meter hogging. Shear force also I showed. Maximum shear force at the rate of support Vu WUL by 2. It comes out to be 32.82 kilonewton. Okay, so now we have to see torsional moment, need for torsional reinforcement or not. So we have to calculate the equivalent quantities as the shear and torsion is acting simultaneously. So need for torsional reinforcement. We will check whether we need torsional reinforcement or not. We will calculate the equivalent shear stress coming from both torsion and shear as well. That is given as shear force plus 1.6 Tu by B. I already wrote it, the formula earlier. BD. Then we plug all the values. So let's assume first we will calculate the D value, effective depth value. D as we will 500 minus, we will assume 30 clear cover, and we will assume 10 mm stirrup and 16 mm bars. That will be 5 by 2 8. Okay, we will get it as 452 mm. Okay, I am assuming first clear cover. For example, this is like this. I have a bar here. I assume this to be 30, and I assume then there is a this 10 5 stirrup, and I assume this to be 16 5 bar. Okay, 500 is the total depth, so effective depth from the top side, from this one up to the centroid, will be 500 minus 30 minus 10 minus 8, 452. When we plug all the values, tau EV is equal to 32.82 kilonewton was this, plus 1.6 times this was 12.20 kilonewton meter, it is 10 power 6 newton mm. Okay, divided by B is 300 mm, divided by BD. B is 300 into D, we already calculated 452. Okay, we will get equivalent stress as 0.722 megapascal. Now we have to compare it with the maximum shear strength of concrete. Shear strength of concrete, for example, if we assume M20 concrete from code, we will get tau C max as 2.8 megapascal, or you can directly calculate it from the formula I told in the earlier lectures, that it is point 0.7 something, 0.7 out root FCK. Okay, you will get 2.8 megapascal. You are seeing that tau equivalent shear stress is less than the maximum shear stress that concrete can bear. So our section is okay. We need not redesign the section. Okay. Okay, now shear strength of concrete. So first we will see what was the reinforcement provided already. Reinforcement provided is like this, where I have shown. Yeah, reinforcement provided is like this. These are 16.5 bars, 16.5 bars, and this is 10.5 at the rate 150 center to center. Okay, this is the basic detail that I want to give. Okay, now we will calculate AST. From this we will calculate AST as area of tension reinforcement. AST as 2 bars into pi by 4 d square is 16 square. Okay, we will get 402 mm square. Okay, so percentage of the tensile reinforcement provided will be 402 times 100 divided by BD. B is 300 and D we calculated as 452. Okay, we will get a percentage reinforcement as 2.296. okay, for 0.296. okay, for M20 concrete and corresponding PT as 0.296. You will look the chart given in IS 456 and from that you will get the shear stress, this shear strength of concrete tau C as 0.386 megapascal. Okay, I have shown you this in the earlier lectures. I will show it again. In the earlier lectures, design of shear. In the shear I showed you. In the shear I showed you how you can find this. Look, you have PT given, you have M20 concrete given, and we were given a percentage 0.296, 0.296. It is approximately 3. Okay, our is 0.296 pt. We can round off it to 3 and we are using M20 concrete, so the shear strength of concrete is 0.388. what I have written there is approximately 0.386. okay, so we are doing it correctly. Now the shear we will have to check equivalent shear stress. Equivalent shear stress is clearly tau V equivalent is greater than shear strength of concrete. Look at tau V equivalent 0.722 megapascal and shear strength of concrete tau C is 0.386 megapascal. So it is clearly greater than from the shear strength of concrete. So we will require torsional reinforcement. Okay, for that we will require torsional reinforcement. So we will check the adequacy of the torsional reinforcement that has been already provided. Okay, so now we will calculate the adequacy of longitudinal reinforcement. Okay, the adequacy of the longitudinal reinforcement. First you have to calculate the effective bending moment, that I provide the formula earlier. Effective bending moment. Okay, mt has a formula tu times 1 plus d by b divided by 1.7. Okay, when you plug all the values you will get 12.20. We already calculated it as 1 plus d is 500, b is 300 divided by 1 over 1.7. We will get a value of 19.40 kilonewton per meter. Okay, so we will have to check the equivalent bending moments. Equivalent bending moment. Okay, equivalent bending moment from 1 me1. If we add this mt torsional plus mu, okay, we will get it as, we calculated mu already. Okay, mt we get 19.14 and mu we got it as, where we I already calculated now, 27.35. okay, 27.35, it will be 46.49 kilonewton meter. And me2, if we can consider this combination, torsional minus mu, okay, hogging moment, this will be 19.14 minus 27.35, so it's coming negative, it will not be considered. So 46.94, from this we will be having flexural tension at top. Okay, so we will calculate ultimate resisting moment. Ultimate resisting moment. Okay, so we will calculate ultimate resisting moment for the section with ASTS. We already calculated as 402 mm square. Okay, for we have formula for that MUR. In earlier classes you studied this formula, 0.87 Fy Pt by 100 times 1 minus Fy by Fck, Pt by 100 into Vd square. Okay, when we plug all the values, 0.87 Fi is 415. Okay, I forgot to write it here as assume M20, F is 415. Okay, 415 into 4, we calculated Pt already. Pt we calculated as 0.296. Okay, 0.296. 0.296 divided by 100 into 1 minus Fi 415 divided by 20 into 0.296 divided by 100. B we calculate is 300, D is 452 square. Okay, when you calculate all this you will get a value of 61.5 kilonewton meter. You will see mu, or ultimate moment of resistance, is greater than me equivalent. This is 46. Okay, me1 from our first combination, me1 46.49, that is the both the combination of flexure torsion. When we consider, we were getting a worst case of 46.49 kilonewton meter, but our section is able to resist a moment of 61.5 kilonewton meter, so our section is safe. Section safe. Okay, this was for this thing. Another thing, we will check education of the transverse reinforcement. Transverse reinforcement. Okay, education of transverse reinforcement. As I already showed in the figure, we have provided two-legged 10-5 stirrup. So we will be having ASV as 157 mm square. Okay, and we calculated, and it is provided at the rate of 150 center to center. Okay, I have already given it as. So we are having SV as 150 mm, and B1 and D1 we will calculate. Okay, B1 and D1 we will easily calculate like this one. So I told you B1 is the distance between the centroids of the longitudinal reinforcement. So we have total distance as B1. So we have one longitudinal reinforcement here, another longitudinal reinforcement here, and this is our section. Okay, like this one. Okay, we are totally given this as 300, and you have to calculate this distance. Okay, that is B1, and these are 16.5. Okay, you are given this here bar as 10.5. Okay, you will get B1 as you will get both clear covers we provided 30. I told you all these details. You clear covers 30. Okay, you will get B1 as 300 minus this 30, this 30, 60. Okay, this 10. Okay, 20, and you will get one bar diameter. You have to deduct 16. You will get as 204 mm. Okay, same calculation for D1. For D1 you have to, from gross depth 500, you have to calculate it, two clear covers 60. You have to deduct the two diameters of stirrup 20 and one bar diameter 16. Okay, you will get it as 404 okay, mm. Please you go through these calculations yourself as well. And another calculation is x1 y1. Okay, x1 I told you it's from the centroid of the stirrups. First one is the centroid of the longitudinal reinforcement, second one is the centroid of the stirrups, x1 and y1. X1 and y1 you will calculate similarly that in the fashion I have shown you above, 230 mm, and y1 you will get as 430 mm. Okay, so B1 D1 already calculated this one. So we will go to the formulas. So ASV required as per the code formula, ASV required will be TU by B1 plus VU by 2.5 into SV divided by D1 into 0.87 FY. Okay, 0.87 FY. This is not a new formula, actually it is just a formula by rearranging the terms here. If you rearrange the terms here, if you take SV common from this and this one and rearrange left hand, bring right hand side to the ASV, you will get a formula for SV. SV is this one. Okay, when you plug all the values, ASV required will be 75 mm square, and we have provided 157 mm square. Okay, save. 157 mm square is nahi ASV provide na, it is two-legged. It is two-legged 10-5 stirrups, 2 into pi by 4 into 10 square. Okay, This will you get. We have to check the spacing also. So as per code SV required is this formula, either x1 or x1 plus y1 by 4 or 0.75d, any one of the three. X1 is 230 already calculated, and this, if you calculate this one, this will be 165 mm, and 0.75d comes to be 339 mm. And I already told you what we have provided as 150 center to center, provided 150 center to center. Okay, so SV provided is is less than SV required. Okay, hence section is educate in all respects, be it the adequacy of the longitudinal reinforcement, or be it the adequacy of the side reinforcement, or adequacy of the transverse reinforcement. And in transverse reinforcement we also check the adequacy for the minimum spacing as well. So we check the adequacy of this section, and the section is safe in all the respects, so the section is okay. So this was all for today. Thank you so much for joining this session. So see you in the next session, week 11. This was all for today. Thank you.